Hello, my name is Patrick Campbell, and on behalf of our collaborators and our colleagues, we would like to present an improved national air quality forecasting capability using the NOAA Global Forecast System, Part 1, Model Development and Community Application. Dr. Yuhua Tang will present later in the session on Part 2, on the science advancements and evaluation. Here I present the introduction and motivation. The National Air Quality Forecasting Capability, NAQFC, has been operational since 2004. There is a transition to the Finite Volume Cubed-Sphere FV3 dynamical core in the NOAA Global Forecast System, or GFS. There is also a major upgrade of GFS from version 15 to 16, and there is a need for streamlined development of GFS-16 for next generation state of science NAQFC. We also want to improve community options to use NOAA GFS-16 products for CMAQ applications. Here, I show the next NAQFC, NACC-CMAQ. In the flowchart at the top, GFS-16 is processed by our adapted NOAA-ARL Atmosphere-Chemistry Coupler, or NACC. This provides parallelization techniques and direct interpolation to feed CMAQ 531 from a GFS-16. Also included on the left are updated satellite inputs, such as MODIS leaf area index and VIIRS greenness vegetation fraction. We also include updated soil surface inputs based on soil grids, clay, sand, and silt. We also have updated chemical boundary conditions based on the NOAA GEFS aerosol model to provide dust and smoke at the lateral boundaries. And on the right, we have updated to EPA 2016 anthropogenic emissions, and also include intermittent emission sources developed at NOAA-ARL, such as the FUNCSA windblown dust scheme and GBB-EPX wildfire smoke. These are also fed into the CMAQ 531 system to provide state of science predictions for 72-hour forecasting at NOAA, but also community science applications. What is NACC? The NOAA-EPA Atmosphere-Chemistry Coupler, or NACC, meaning an acquired skill, is adapted from the EPA's Meteorology Chemistry Interface Processor, or MCIP, version 5. NACC couples the FV3 GFS-16 with the Community Multiscale Air Quality model, version 5.3.1, as shown in the previous flowchart. NACC is being developed for NOAA's operational NAQFC and is available to the greater scientific community at the GitHub page shown here. What are the advantages of NACC-CMAQ? Not only does NACC-CMAQ interface NOAA's GFS-16 with the latest CMAQ 531, it also processes high-resolution satellite vegetation and soil data inputs for CMAQ. It has user-defined vertical layers and can run CMAQ with native GFS or collapsed layers. The GitHub integration allows for streamlined future updates to NACC-CMAQ as new versions become available. It has advanced intermittent emission sources and aerosol boundary conditions. And the NACC parallelization with MPI speeds up I/O drastically and is easily portable to other systems. Here I show the fundamental NACC structural changes. On the left are the directly interpolated fields by NACC, for example, from GFS-16 surface temperature at about 13 kilometers to NACC at 12 kilometers below that. As you may see, there is good agreement between the GFS-16 and the NACC, and there is no downscaling needed for CMAQ. On the right, I show a redefined vertical structure by NACC, where the first panel on the right, GFS-16 in green, has higher vertical resolution and a thinner first layer, about 20 meters, than previous GFS applications. And on the far right, NACC can use either native or collapsed GFS-16 layers, and there is good agreement in the structure, as shown here in the temperature line in black and the dew point line in blue, and also the winds on the far right. In the next section, I will highlight some other NACC-CMAQ advancements. Here I show an updated satellite land cover characterization, where currently NACC-CMAQ uses a 12-month MODIS LEI climatology and a NOAA weekly VIIRS GDF product. The plan is for NACC-CMAQ to eventually also use VIIRS LEI product instead of MODIS climatology. On the left is MODIS leaf area index, and on the right is the VIIRS greenness vegetation fraction for August 2019 at 12 kilometers after being processed by NACC. An example on the right, as you may see, the VIIRS greenness resolution is 4 kilometers, and it's a high resolution, and thus allows for more detailed representation of the greenness vegetation fraction, where the idea is that more dynamic land cover changes will be used to improve air surface exchange and deposition processes in NACC-CMAQ, and is currently undergoing testing in real-time simulations. Another NACC-CMAQ advancement is the incorporation of the FUNCSA inline wind-blown dust emissions. Governed by the main equation on the top left, the flux of dust, F, is strongly controlled by the soil erosion potential and sources, the surface friction velocity, U star, and the difference in the surface friction velocity and the surface threshold velocity. Therefore, FUNCSA is strongly controlled by the soil properties. And NACC processes these soil properties and is currently using the high-resolution soil grids 250 meter data shown below on the left, where the derived soil type, a function of clay fraction and sand fraction, and also is provided is the sediment supply, drag partition, and threshold velocities, all which can be easily refined outside of the code. On the right is an example for the Phoenix, Arizona dust event in August 28th and 29th, which occurred overnight. On the bottom right, I show animation of NACC-CMAQ with no dust on the left and with NACC-CMAQ FUNCSA inline dust on the right. Preliminary results show that CMAQ agrees well when including FUNCSA inline dust in the timing of the event and also the magnitude with the AirNow PM10 overlay. Wildfire smoke has a significant impact on human health. In NACC-CMAQ, we incorporate the Global Biomass Burning Emissions Product, or GBB-EPX, for the wildfire smoke emissions. The GBB-EPX version 3 algorithm estimates fire radiative power, FRP, which can be used as a proxy for wildfire smoke emissions, using the active fire observations from MODIS and VIIRS, which are polar orbiting satellites. On the top left, I show an example for daily PM2.5 global wildfire smoke emissions from GBB-EPX for July 8th, 2019, and on the top right, a more zoomed-in view of the Williams Flats fires, which occurred in Washington State on August 7th, 2019, where MODIS and VIIRS pick up the fire pixels nicely and show the transported smoke to the east, where GBB-EPX indicates a high value of the associated FRP for those fires. GBB-EPX is being tested at 0.1 by 0.1 degrees input in a real-time PM2.5 forecast, where, on the bottom, there is initial improvement over the operational NAQFC HMS Blue Sky method. We are currently testing more cases during the 2019 FireX-AQ campaign between NOAA and NASA, and I encourage you to please see Dr. Pius Lee's talk in the Wildfire Emissions and Air Quality session for more details on NOAA's GBB-EPX wildfire emissions. The final NACC-CMAQ advancement, highlighted here, are the incorporation of dynamic aerosol boundary conditions, which are based on NOAA's Global Ensemble Forecast System aerosol member, or GEFS-aerosol. This is based on the go-kart mechanism. NOAA's operational GEFS-aerosol member provides dynamic lateral boundary conditions daily for smoke and dust aerosol sizes to the regional NACC-CMAQ domain. And on the left, I show an example for the extreme Saharan dust storm of July 2020, which transported an abundance of dust to the west and impacted the U.S. domain. An example on the right for the impact on CMAQ PM2.5 is for a case of wildfires around Mexico City, as shown by the VIIRS image here on May 14, 2019. On the bottom right, I show an animation for the static lateral boundary conditions on the bottom left and the GEFS dynamic lateral boundary conditions on the bottom right, where, as you can see indicated by the arrows on the bottom right, wildfire smoke intrusion across the southern boundary improved the CMAQ PM 2.5 predictions, increasing the IOA, or Index of Agreement, in EPA Region 6, which is the southern U.S., and demonstrates the importance of incorporating dynamic aerosols at the lateral boundaries. For the final section of my talk, I will present on community applications and research with the NACC-CMAQ system. Typically, the Downscale Weather Research and Forecasting Model, or WRF, is coupled to CMAQ for research applications. However, NACC-CMAQ is a new research option for direct coupling of NOAA's GFS-16 to CMAQ and avoids downscaling and running WRF. I show here an example for averaged August 2019 ozone, where on the left, GFS-16 is downscaled to WRF version 4, input to CMAQ 531, where the WRF downscaling uses different GFS versus WRF physics to CMAQ. Whereas on the right, GFS-16 is directly interpolated through NACC to CMAQ 531, and there is no downscaling, and there's direct GFS-16 physics input to CMAQ. What we can see is that this demonstrates generally improved model performance of NACC-CMAQ compared to WRF CMAQ for this configuration. The bias is significantly reduced and the error is significantly reduced, and there is improvement in the index of agreement. For the same comparison, but for August 2019 PM 2.5, NACC-CMAQ demonstrates generally improved model performance compared to WRF CMAQ configuration. However, there is slightly degraded index of agreement, and we are actively working to improve NACC-CMAQ PM 2.5 predictions, particularly the diurnal pattern with CV6 Aero 7. I encourage you to see part 2 of this talk, Dr. Yuat Tong, on the science advancements and evaluations for more details on the WRF and FP3 GFS configurations and more of the evaluation details. Up to this point, we have shown preliminary results of NACC-CMAQ and compared those results to WRF CMAQ. To expand our community applications and research, we are developing a prototype for NACC input-output data to be available in the cloud on a server such as Amazon Web Services, AWS. This would facilitate GFS-driven CMAQ applications for the greater research community, thus allowing access for CMAQ-ready NACC outputs for NAQFC domains that are pre-generated, or accessing the GFS inputs themselves to run NACC in the cloud for any user-defined domain globally. This may have many potential benefits. To interface directly with a NOAA operational GFS global dataset with no data download required. It may form a new research tool for any regional domain globally and avoid downscaling and running WRF. And for forecasters and researchers, rapid applications of CMAQ-ready meteorology for recent air quality events and applications. Again, NACC is available at our NOAA-ARL GitHub page shown here. Here I present a summary of this presentation and our ongoing work. The next generation FP3 GFS-16 NACC-CMAQ system is developed. The NACC-CMAQ system has numerous advantages over our current NAQFC. NACC-CMAQ is currently being run experimentally in real time at NOAA, and continued advancements and refinement tests are being done. These include updated satellite land cover and use, wind-blown dust emissions, and wildfire smoke emissions. NACC-CMAQ is scheduled for implementation at NOAA in January 2022, and the early NACC-CMAQ performance shows consistent or better performance than WRF-4 CMAQ applications. NACC-CMAQ may be used as a new research option to avoid WRF downscaling, and there is potential for NACC in the cloud and user-defined GFS-driven CMAQ applications. Finally, We would like to acknowledge Tanya Sparrow and the US EPA for their many years of development and collaboration on the PREMAC and MSIP systems, which were pivotal to the development of NAC in this work. Thank you all.